This question is titled, What is recursion? What is divide and conquer? Well, it turns out that if we want to think through a dynamic programming problem, we'll see as we work through enough of these that there's a very, very common pattern to them. And one of the key points of at least the operational mechanics of how we write either some memoized function, this top-down or this bottom-up, is the topic of recursion and how we can turn recursion into something where we can exploit efficiencies from what we'll soon learn are overlapping subproblems. Why don't we take a look? Generally, one thing that we'll discover is that recursive formulations, they all just about look the same. There's some base case and there's some inductive step. And I like this phrasing, inductive step, because what you can think is, using something similar to mathematical induction, we can demonstrate that the solution to a problem is starting from some very simple answer and then inductively expanding that to all the possible answers. A very common example of a recursive formulation is something like a binary search, your common classic divide and conquer algorithm. We can say that at its core, our base case is the idea that we have an empty structure. Well, I can tell you whether an element, a needle, is in an empty haystack. That's always false. Or a structure with, one element where, or with one or more elements where the needle happens to be exactly that middlemost element. That's another one of our base cases. And I can tell you, well, if it exactly matches, then we found the thing. That's a true. And then I can derive some inductive steps. And I can say, you know what? I can start with this core, this kernel of the answer to the problem, and I can build up to any possible input data set by just decomposing that input data set into smaller problems, and then decomposing those further into smaller problems, and so forth and so on. And so I have my inductive step here. And so you can see even in this binary search, we have our base case and our inductive step, and they're actually fairly easy to see. The inductive step is typically the step where you're then going to recurse back into the function. And so if we run this code, if we try it with a little bit of a test, we can see everything seems to work exactly the way that we want. And we've been able to solve this problem by breaking the problem into smaller subproblems. This is the core reason why we might use recursion. We might say that instead of trying to define holistically over the entire data set what the answer is, we want to define at the smallest scope what the smallest, narrowest answer might be, and then delegate our work to some subproblem. And you may even think, this comes up even beyond some of these algorithms. It's very commonly the case that whenever you're doing some sort of object orientation in Python and you're implementing something like len or implementing something like iter, you may delegate that work back to the protocol. You might say, oh, the len of this thing is the len of some data that this thing contains. And you can see here, it's very likely that this may be some recursive call because that might then itself recurse and then recurse and recurse and recurse until somebody answers the question. And when you think about things like the Python data model, what you can think is the whole reason that you chose this formulation in the first place was because you didn't want to define what it meant to answer this holistically. In the totality of the universe, what does it mean to find the length of some structure? How many bits is it? How many entries in some contiguous C storage? You just say, you know what? I'm just going to decompose this into a problem that I know somebody else can solve. So when you ask me how large this object is, I'm just going to say, you know what? It's however large this one element of this object is, this one constituent piece of this object is. And we often see that this is the case whenever we're doing something with the Python object model, whether it's delegating to a constituent component, an attribute, or whether it's delegating to a subtype, whatever the case may be, we're oftentimes defining an answer in terms of an answer to another question. Now, if we return to our binary search, and we see very clearly this base case and this inductive step, well, how does that really help us with anything? Well, being able to spot this pattern is going to be key to another transformation that we want to be able to do. Because there's a lot of really trivial recursive problems that we can write up and we can solve. Factorial is another one. Here you can see very clearly the base case and you can see the inductive step. But the real goal here is not necessarily to be able to spot the parts of the code in that fashion, but to realize that recursion doesn't actually exist from an operational perspective. Recursion is something that's kind of interesting because we can see this pattern. We can see this pattern repeating along many of the problems that we might want to solve. But the question is does it exist in terms of how the code is executed? Well, let's think about how code is executed at the lowest level. You have some program counter, a PC, and that program counter points to a memory address and says, I'm going to run that instruction at that memory address. And it then increments the program counter and says, OK, I'm going to run the instruction at the next memory address and the next memory address. And this is a fairly realistic model of how computers worked, at least as of the late 80s. Our modern computers are a little bit more complex, but we still have that pretty basic idea. If you think about this, this is basically the idea of your Turing machine, your long tape with a read head that just jumps from instruction to instruction to instruction. Well, in that simple model, everything is just run some code, increment the program counter, run some code, increment the program counter, maybe tell the program counter to decrement itself or to jump somewhere else, run some code, jump somewhere else, run some code, jump somewhere else, go back to a previous instruction, whatever the case may be. And if you think about that mechanic, where does really recursion fit in there? Well, the answer is it doesn't. Operationally, mechanically, recursion doesn't really exist. The way that recursion is actually implemented is we have to start with the idea of reentrance. And this is something that really doesn't come up that much these days, but was a topic of great interest in the late 80s, early 90s. The idea that if we have some function, can this function call itself? Can this function re-enter itself? And if you think about the simplest possible model of computing, minus virtual memory, minus operating systems, just a program counter running instructions at a fixed memory address, well, you can think that we have some memory address, and then we have the code for f here. And these are all the instructions corresponding to the code for f. Our program counter says run this piece of code, run this piece of code, run this piece of code. We might jump somewhere else. So if we called g from f, then there might be some instruction that says, OK, do a jump to whatever the address is for the code for g, and we proceed from there. Now, if it's the case that f has some local variables, well, where do we actually store those local variables? In the historical view, what we would do is we would carve out a little bit of space around where the code for f was to store the local variables. So here would be the code for f, and here would be like the local variables for f, and a little bit of storage space here. So this would be the storage space for x and the storage space for anything else. And here would be the actual instructions that we'd run. And when we jump into G, we have this fixed memory address for any local variables that G refers to. But it seems pretty clear from this that if we actually had it the case that, and let's give this a flag. So we'll say if mode, we'll jump into here. And then here, we'll jump back into F. And here, we'll set the mode equals to false. By default, we'll have this equal to true. So that way we don't keep going back and forth. We don't cycle forever. Well, what you can think is, if this variable happened to be updated or changed on the second entry into F, like if we print out that we're in F here, if this happens to change on the second entry to F, well, if we only have one spot in memory where we locate that, this is going to be a problem. We're not going to be able to, have multiple values. We're not going to allow this function to re-enter itself. And so if, for example, there was some value here that we pass in, and this is computed off of that value, and we're going to look at what that value is, and here we call g, and then maybe g calls with a new value, 1, 2, 3. Well, how do we maintain two distinct values for x for both of those invocations if it's the case that we only have one spot in memory? And remember, after we're done calling g, we might want to continue operating in the scope of this function. So we might want to make use of what the value of x was before we perform that call. And we'd never be able to go back in time. We don't have that history available to us. If we've only got one spot for storing this, we don't have any history. And so the revolution that allows us to be able to do this is the idea that the local state of a function that we're running is not stored as a fixed location in memory, but it's stored as some structure that gives us a notion of the history of all the functions and all the local variables they've called. And whenever you think history in Python, well, you should think about our friendly built-in type, the list. The list is a way for us to represent some unbounded history of elements. If we want to add another piece of history, we just append to the end of the list. And if we want to remove a piece of history, we just pop. Well, if you look at the behavior here, and you look at the order in which the elements are being added and removed from this list, you might say, oh, these are being added in a last in, first out order for this history. This is a stack. Fundamentally, what took us from non-reentrant functions to reentrant functions was the introduction of a function called stack, or a stack where we store the local variables. What you can think is happening in the case of this function that reenters itself is, instead of storing these local variables in one singular location that will then be overwritten if we re-enter, what's going to happen is we're going to extract that storage to some stack, and every time we invoke f, we're going to add to the stack some storage space for the local variables for f, and then some storage space for any of the local variables for g, and then we re-enter f, we're going to have some separate storage space for the local variables of f. When we leave this, we'll pop this off the stack, pop this off the stack, and pop this off the stack. So we get this idea of history that can grow in one direction and then shrink in the other direction. It grows in the direction of function calls, and it shrinks in the direction of function returns. And this is fundamentally how any sort of function call mechanism works, either in Python or in C. This is how it works in the modern era. There is one very, very slight difference to how this might work in C or C++ versus how it might work in Python. And the very slight difference here is, even though the mechanism of when you enter a function and when you return from a function is that first in, last out structure, that last in, first out structure, that stack, Python doesn't actually use a function call stack in the same way that C or C++ do. In fact, all of the frames that store all the local variables for a Python function are heap allocated, which means we can actually take a look at the local variables of a function after the function has completed running. So here, let's do this. Let's actually give this a local variable like that. We'll call g with this local variable. We'll create a g here. We'll give this a local variable. And we'll call h with that new local variable. And in h, we'll take another variable here, and that would be, let's say, z. And then we'll create one more local variable here, which is z cubed. We'll fix our typo here. And then here, we'll just return that. And if we call this, we obviously kind of know what this is going to do if we give it some input value. But one of the things we can do, of course, we'll have to fix our imports, is at each stage, we can actually ask the stage for what its current frame is, where that storage for these local variables look like. And we can ask that current frame for its local variables. And we can actually return those as we go up. So we can go all the way down to h here. And we can say, don't give me your current frame. Give me all the frames that led up to you, like that. And this will give me the frame for h, the frame for g, and the frame for f. And critically, I'll be able to see all of those from the outside. Now here I'm running with an IPython kernel, so I probably need to trim this down to just some of the ones that I care about. And you can begin to see if I create a list comprehension from these, I can get the function name. So I believe there's only 3 of these. So let's do this. Let's do frames function for x in frame. And you can see that's the FGH function call stat, or the function call, or the code graph, as it were. And I can look at the local variables for these. I think I might have to do frame.flocals here. And you can see all of the local variables that exist at each level. These actually persist. These exist outside of the scope of the function. This is how things like generators and coroutines work. But fundamentally, what we can think is, because these mechanisms don't really exist from the execution perspective, but our code still runs, there is necessarily always a way to take some recursive formulation and to turn it into an iterative formulation. And the key to that is basically doing exactly what the machine is doing, creating an explicit stack. In other words, we can think that whenever we're given this dichotomy between is there a recursive formulation or an iterative formulation, and we say, oh, we don't want the recursive formulation because in Python we have a recursion limit and all of those details, what we're really trying to do is trying to change one way that we as a human being write out the code to another way that we as a human write out the code. And the key change here is taking an implicit stack, a stack that exists that we can't see, that in C or C++ would be the function call stack, in Python would be the call stack, even though the underlying frames are heap allocated, and turning that into an explicit stack. And that gives us a natural mechanical transformation. Every single recursive formulation can be turned into an iterative formulation by just making that stack of the local frames visible. Let me show you an example of that. Here we have our factorial function. And this factorial function is not implemented recursively. Instead, every time I would otherwise call down to the next iteration of this, to the next factorial function, I'm just going to add a frame, just some local storage, a dictionary in this case, to a chain map of these. And to simulate the return process coming back out, I'm just going to pop these off. And so here, this append left and this pop left, that's basically what's happening behind the scenes with those frames that we saw before. And this allows us to solve this problem without actually needing recursion. Now, this is a very clumsy transformation. And in fact, this transformation has some things that are maybe not that great about it. But fundamentally, what it shows is every single formulation of this type can be implemented in this particular fashion, or at least we can decompose it into this fashion. And once we decompose it into this fashion, we can always then find some places where we can tidy up the implementation a little bit. Like we could say, you know what, I actually don't need to store, I actually don't need to push and pop because I'm really just reusing the same data. And in fact, if I'm doing that, I probably don't even need an explicit stack, so I only use one particular position of that stack. I never really refer to anything prior to that, which means I can now implement this thing in this fashion, which, according to my test, as long as, of course, my syntax still works, according to my test, crossing my fingers, should still work. Here, we don't even need the stack at all. And one of the things that we could reason about this is, for the factorial implementation, it is tail recursive, and one of the characteristics of a tail recursive function is you never look at any of the previous values. You just do something and then carry that forward. You never need to go back to the previous history, so you don't need to store the history, so you don't actually need to have the whole stack. You just need to have whatever's on the top of the stack, and that's basically the formulation here. Now, performing this recursive to iterative formulation is oftentimes a little bit harder than this and a little bit clumsier than this, but what I want to show you is it is always possible to perform that transformation. And this is going to be a key point when we discover what it means to talk about things like overlapping subproblems and where things like memorizations or the tabularization approach in dynamic programming come up. Ultimately, we can always consider some recursive formulation to have some implementation that does not recurse, but instead uses some explicit data structure at our level in order to implement the mechanics that we want. Now, this gives us a starting point. Divide and conquer algorithms are any algorithm where we can break the problem down into smaller parts and break it down into smaller parts and break it down into smaller parts. If we think back to our discussions of Big O, oftentimes divide and conquer algorithms are about splitting the input into halves, and that gives us probably log n complexity because we split it in half, split it in half, split it in half, and then solve it on the smallest unit we can, and then carry that answer back up. Divide and conquer algorithms are almost always at least formulated initially in a recursive fashion, but that recursive formulation is always available for reimplementation or through some mechanical process to be implemented without recursion.